Well, Mr. Sam's,
Nice hat.
I think you like the hat. Well, you know what? It snowed some last night here in Woodland Park.
It did.
And we just got in here, and it's like, what time is it?
I don't know.
6:45 in the morning. So we are getting this done just in time. Mr. Sam's putting on his hat. It's like cold.
It's cold.
Very cold. So we are, of course, interested in staying warm. You know, we're going to talk about temperature today.
We are a little bit, yeah.
We're going to talk about how temperature
affects equilibrium.
In fact, the only way to change the equilibrium
K
constant,
value.
Yeah, the K value is to
Change the temperature.
Change the temperature. So the temperature got colder today, which made it kind of like an endothermic thing, and yeah, so this kind of it fits. So today we're going to talk about two things: equilibrium calculations, and we're also going to talk about got the calculator.
Get your calculator out. Follow along.
Yeah, we're going to teach you how to use the solver today.
Oh yeah, it's the solver.
So solver day, and then we're going to talk about Le Chatelier's principle. Le Chatelier. I love that name. Isn't that the coolest name?
It's pretty good.
French dude. Le Chatelier. All right. Well, let's have at it. Okay?
Alrighty.
All right. Okay. So as you can see here, goes. Here we go. All right. Go forward. Come on, my thing is not working. Ah, there we go. All right. We're going to start learning how to solve equilibrium calculations. Okay. How do you solve equilibrium calculations? Well, you start with the balanced chemical equation. That seems like a lot.
Yeah, can't do much stuff.
It's kind of like stoichiometry, but on steroids.
Yeah.
Write down the amounts. You can use what's called an ICE table. We'll do example that. Show you that? It's early.
We'll
Show and tell. Shift the equilibrium by subtracting and adding x to either side of the equation. Solve for x using the solver. Today we're going to do solver learning. This is the coolest thing on your calculator you can imagine, guys. And sometimes they have to be solved in reverse. We'll talk about that as we go. All right, so we have some sample problems. Let's go. The equilibrium constant for the following reaction is 0.09. We got a reaction. So now what we want to do is we want to determine which direction it will shift, right? So this really isn't an ICE table problem.
Nope.
We actually know the concentrations, or actually these are pressures. So let's draw or write the equilibrium expression. So we have a reaction, water plus Cl2O here, and so let's actually just rewrite that. I think that would be best. So what's the reaction, Mr. Sams?
Water
plus
Cl2O
makes
2 HOCl.
2 HOCl. Now what do we know about this? What are our numbers, Mr. Sams?
The pressure of water is 200 torr.
200 torr.
Pressure of Cl2O is 49.8 torr.
49.8. And the
And
HOCl?
the HOCl is 21 torr.
21 torr. Now the K, in this case, we would do a Kp because these are given in pressures, would of course be the products over the reactions. So the partial pressure of the HOCl squared divided by the partial pressure of the water, that'll be the first power, times the partial pressure of the Cl2O squared.
Yep,
Now
and the K value is given.
What was the K value?
0.0900.
So what we're going to do is we're essentially going to plug in these numbers and compare it to this number, and then we'll talk about what it means.
Yep.
So our value of the HOCl was 21, right?
It was.
So 21 squared. You get the calculator out?
Yep.
Over
I've already got it calculated.
200. Oh, you're amazing.
Yeah.
Times 49.8. Actually, this is not squared, is it?
The Cl2O is not squared now.
Yeah, my mistake. Okay, what did that come out to be, Ms. Sams?
0.044.
So that number is smaller than 0.09.
I guess 0.0443 with sig figs.
Okay. But the point actually,
Yep.
it doesn't matter what it is,
Yep.
except that it's bigger or smaller or equal to 0.09. So if the number is smaller, the question is asking which direction will be favored or something to that
Which
effect.
direction will it shift? Okay, we're calculating something called Q here, folks. When you're given conditions that are not at equilibrium, there's some given conditions. You just plug them in, and it tells you what's called the Q, the reaction quotient.
Right.
So since that value is smaller than K,
Right.
what that means is that the denominator is larger or the numerator is smaller. Either way, we've got more reactant and less product than we do at equilibrium.
So too big on the bottom.
Too big on the bottom, which if we have too much reactant, that means it's going to shift right in order to reach equilibrium.
Because you need to make more product or less reacted, depending on which would, of course, make more product. So it needs to shift to the right so that it becomes and equals 0.09. If we kind of went back to our boy-girl analogy, and makes couples or whatever, is that if the ratio of boys to girls to couples should be 0.09, the problem is we don't have enough couples.
Yep.
So we're going to make some more couples. So anyways, that's it. All right, let's do essentially the same example 1. This is example 2. Same exact thing. We got different numbers, however. So we have our same reaction, which is H2O plus Cl2O makes 2HOCl. And so we can just say the the K would be equal. They were all 1s, weren't they?
Yep, all 1s.
So this would be 1 squared.
Not really K, it's Q.
Equals, yeah, that's true. Thank you, Mr. Sims. I don't really need a calculator for that.
No, that's 1.
That would be 1. Now this number is much, and then if you recall, K is equal to 0.09. This is much, much bigger than it should be, so we've got too many couples, if you will.
We've got a bigger numerator and a smaller denominator, so we have too much product, not enough reactant, so it's going to shift left.
To shift left. So some of these questions are just shifting type questions. And then question C, we have the same thing here, except we have different values.
Yep.
And so, hello. We need some blank space. We'll just do it here.
Yeah.
Hold that thought. So we're going to say Q would be equal to
20 squared.
20 squared over
296.
296.
15.
Times 15. And I think I actually know what that is in
It's
my head.
0.0900.
I think it's 0.0900.
Yeah.
Now, what's going on with that is this, of course, is
it's at equilibrium.
at equilibrium. So since it's equal, it's at equilibrium. Okay?
Alrighty.
Very good. How about example 2? Now we have an equilibrium constant for another reaction, and this is the value. And we know the initial concentration of the hydrofluoric acid. What is the final concentrations of all things established?
All right, this is the ice box.
Yep. All right, let's write the reaction. We get 2HF breaks apart into H2 plus F2. Now, what does this ice box mean, Mr. Sam?
The IC stands for initial, change, and equilibrium. So the initial concentrations, the change that it undergoes, and then the concentrations at equilibrium. So this one we have 2 molar HF to start, and we have none of the products.
All right, so what direction is this going to shift?
Well, it has to shift right because there's nothing over there.
Yeah, it has to shift to the right because, yeah, you've got to get a number, whatever the number was, you have to get it to shift to the right. So it's going to diminish by some amount, but we don't really know the amount, so let's call it
X.
And the C stands for the change. It's going to change by some amount, let's call it X.
It's actually not going to be X.
Actually, that's a good point. It's going to diminish by
2X.
2x, because it's actually important to know that we have a coefficient right here. This will increase by x. It'd be 1x because of the 1 here. By the way, if there's a coefficient here, 3x or whatever, or 3, then it'd be like 3x. This is just going to be plus x. And so the amount at the bottom here will 2 minus x. This will be
2
x.
minus 2X.
2 minus 2x. I'm still waking up. Okay.
Boy, and you're the morning person.
I know. This morning, my daughter was up all night. Okay. So, now we can now use our K expression. Now our K, now this would be a C because we're dealing with molarities or concentrations, would be equal to the concentration of the hydrogen times the concentration of the fluorine over the concentration of the hydrofluoric acid.
You know one thing we didn't talk about in our last podcast, Mr. Bergman? About the states of all the things in the equilibrium expression.
Oh, that's a good point.
Needing to be the same.
Yeah, that's important that they are in the same state of matter. These are all gases. Yeah, they have to be homogeneous in their states. We should maybe go back and add that. We'll think about it. Okay. So, now I just plug in some numbers. Actually, first of all, I do know the value for this. What is the value? It was given in the
K
problem.
value 1.5 times 10 to the negative 5.
Now I'm simply going to plug in my x values and this, whatever, into the appropriate thing. So just plug and chug. This will be x times x over
2 minus 2x.
2 minus 2x. Not exactly. 2 minus 2x squared. Now I want to find x.
Yep. Now we got to do some algebra.
Yeah, we do some algebra. Now this is like got squared terms in it. So we would take 1.5 times 10 to the minus 5. I'm going to cross multiply. Times that by 2 minus 2x squared, and And that would be equal to x times x, or well, of course that's just x squared.
Can you get rid of that x there for me?
Oh yeah.
That's not really part of the equation.
Yeah. So now what's x? Ooh.
All right.
Ooh, nasty. Is that kind of like a hard? That's like. It's the quadratic formula.
Yeah, we could use some quadratic. That's ugly. We don't want to do quadratic,
Like
especially
negative
on
b
the
plus or minus.
when you're taking the AP test. The last thing you want to do is to whip out the quadratic equation.
Yeah.
It'll take forever.
There is a cool shortcut we can teach you. It is called using the solver feature of your calculator. So everybody, if you have not already gotten your calculator out, maybe get your calculator out right
By the way, you
now.
need graphing calculator has the solver.
You can't have a cheesy little cheapo calculator. You need a real calculator. So get that out.
A real calculator.
And we'll show you how to do that. Okay, so here we have the equation on the screen, and I want to use the solver on the calculator. So here I have my TID4 Plus, and I want to use a button, the math button. So you're all going to push the math button. And now the math button has, if you look at the screen right here, lots of things, cubed root and such like that. What you care about is the solver. So this is the 0 button. Actually, you could just push math and 0. That'll get you there. Then I push enter. Now I have a whole bunch of gobbledygook right here. Now if you have that, what you may want to do is you may want to arrow up. Because what I want to do is get what's called the equation solver. And I've got an equation already in there from some other thing. So I'm going to just clear it. So I push clear, and now I have equation 0 equals. Now when I have equation 0 equals, that means I need to rewrite my equation such that I can get it set equal to 0. So if we go back on the screen here for just a moment, essentially if I've got this equation I cross multiplied, I can essentially subtract x squared from both sides. So I'm going to take 0 would be equal to 1.5 times 10 to the minus 5 times 2 minus 2x squared minus x squared. So I'm going to now type this into my calculator. So watch how I do this. I'll type 1.5 e, second function e, was it minus 5? Negative 5, parentheses, that's the times, 2 minus 2. Now the x button, if you don't know, is right next to this alpha button right here. So I push the x button, parentheses, squared, minus x squared. Good? Push enter. And now, now I have this thing, and I've got an x here. X is actually where you would type in a guess. I want to pick a particular number. Now, if I look back on the screen here for a moment, there's kind of a bound for x. If you get 2 minus 2x, it can never be less than 0. I mean, it can in the real world, but in the mathematical world, our concentration or our pressure, whatever this was, concentration can't be negative. You can't have a negative concentration.
I always use 1% of my initial value. So we started with 2 molar.
Yeah.
So I always do 1% of that.
So 0.2 or 0.02.
Right.
So 0.02. And now what I want to do is I actually want to push the solve button. Now the solve button is down here. It's kind of a function of the enter button right here. It's the green here. So I'm going to push the alpha and then the enter, or alpha solve. That's what I usually say, alpha solve. And what it's doing is it's guessing and checking and guessing and checking, and guess what? It gave us an answer. And it says the answer to x is 0.0077. So that's x. Isn't that cool? Now if you recall, the concentration of the hydrogen was the same thing as the concentration of the fluorine, and they're equal to x, which is 0.0077 molar. However, the concentration of the HF, that was equal to 2 minus 2x. Now let me show you something just so amazing. I'm going to quit out of the solver, second quit, and I'm going to take 2 minus 2x, because it's actually remembered the calculator what x is. I push enter, and that's 1.98. So those are the final concentrations of this, and we've taught you how to use the cool solver. Isn't that the greatest thing since sliced bread, Mr. Sims?
It's amazing.
It is so, so cool.
Now, by the way, if you don't have a graphing calculator, there's another way to do this without having to solve for x using horrendous mathematical equations.
Yeah.
Should we talk about that real quick, just in case they don't have one?
So what you could do, Mr. Sams, what would you do?
Well, it's something called the small x assumption. So let's go back to the original, when we had it set up, where we had k equals, so the products over reactants. So 1.5 times 10 to the negative 5 equals x squared over 2 minus 2x. Now the small x assumption basically tells you that the amount of the initial that you're going to lose is very, very small. So x is small, So what we do is we just ignore that 2x term.
So then you just write 1.5 times 10 to the minus 5 is equal to x squared over 2 squared.
Yeah.
Now, by the way, this only applies if this number right here, if the k value is a small number.
Right.
If the k is a big number, small meaning less than 1, significantly, 10 to the minus whatever. So now we just solve for x.
Right. Now it's pretty simple, and you can do that. You'll get within the answer of 5. You'll get within 5% of what the answer should be.
Yeah.
And also, the AP test accepts this method as a valid method for solving for x. So if you don't have a graphing calculator, use the small x assumption. Check to make sure your answer is in fact less than 5% of the initial value, and that's a safe assumption to make, and it's acceptable.
Okay. Let's do, I believe we got one more. This one is one where you would not want to do the small x assumption. I think we got a typo here. There'll be double arrow right in here. So we have some numbers, okay? And so let's rewrite this equation. What was the equation?
N2
plus 3H2
plus H2. Yep.
We didn't.
Not balanced,
it's not balanced. We'll balance it. That's easy though. So N2 plus 3H2 makes what? 2NH3.
Yep.
Now what do I know now?
You know that the K value is 4.35.
4.35.
And the initial value of N2 is 2.3.
2.3.
And the initial value of H2 is 1.25.
1.25. So this will be my initial conditions, ICE, and this is 0. So this will be minus x minus 3x, because you got the 3 here, and this is going to be plus 2x. Now, by the way, I knew it shifted to the right because I had 0 on one side.
Yep.
So this will be 2.3 minus x. This will be 1.25 minus 3x, and this will simply be 2x. Now my k value, I think this is a kc, right? Yeah.
Yeah.
Is 4.35, but that's equal to the concentration of the NH3 squared over the concentration of the nitrogen times the concentration of the hydrogen cubed. Now if I plug that in mathematically, that'll be 2x squared over 2.3 minus x parentheses times 1.25 minus 3x cubed. Now this one, Mr. Sams, you've got to use your solver.
Yep.
Because this is a third order polynomial, and you might be able to solve it by hand, but
speaking of which, you wouldn't get one of these on the equilibrium section of the AP test.
no, but let's just show you how to do it on the solver.
Yep.
Let's use the solver again, I think. And so let me just rewrite this so we can kind of have two screens. So here's my equation right here, folks. And so what I want to do is I need to get it set to 0. So I'm going to just cross multiply. So 4.35 times 2.3 minus x times 1.25 minus 3x cubed is equal to, actually I'm just going to write that 4x squared, because 2x quantity squared is 4x squared. This is kind of an ugly question, isn't it? So I'm going to subtract 4x squared from both sides. So 4.35 times 2.3 minus x times 1.25 minus 3x cubed minus 4x squared equals 0. So I'm going to try and solve for x again.
Yay, solver.
This is where you just don't really want to mess with the math.
No.
So math and then 0. Now I still got all the gobbledygook from the previous problem we just did. I arrow up, use the arrow up here, and I'm just going to clear it out. I'm going to retype it. I'm going to just type it the way it looks like on the screen there. So 4.35 parentheses 2.3 minus x parentheses 1.25 minus 3x parentheses. Now I got to cube it, so that's this caret button right here. Caret 3, and then I'm going to subtract 4x, and I do have this squared button. So it's a complex equation. It just looks on the screen here, just like it should look on the screen right next to you. Push enter. And now the guess, actually, Mr. Sams, your little guess method is not going to be as good.
Not as accurate here because it's a big K.
Because
value.
K is big. 4 doesn't sound like a big number, but compared to 10 to the minus 5, it is. And so I'm going to say, if you look on the screen,
I'd say like
1. Yeah, I'm going to call it 1. Let's just make a guess of 1. If you make a missed guess, that's not a problem. I just do second. No, I don't. I do alpha solve. And I got to be in the right spot. Okay, alpha solved. It's thinking, it's thinking, it's thinking. Answer is, x is
0.30.
0.30. So, now the concentration of the NH3 equals 2x. So I'm going to quit right here and say 2x, and it's 0.602. The concentration of the hydrogen, which one was it? And the concentration of the
hydrogen is 1.25.
That's the 1.25. Okay, this was 1.25
3x.
minus 3x. So I'm just going to type 1.25 minus 3x, and I get 0.35. 0.35, and the nitrogen
was 2.3 minus x.
So I'll just say 2.3 minus xer. 1.9, call that 2.0. And these are all molarities. Boy, and that's, folks, that's the answer.
So those are the concentrations of those things when the system reaches equilibrium.
Correct. And those would be the answers to the question. All right. Good? All right, so we will call that, yeah, so let's do example 4. So we got example 4 right here. We have a reaction. Actually, there should be a double arrow between here and here. And so we will figure this out. So let's take a look. Here we have a reaction. I actually just had to print it up so I didn't have to recopy it. You probably need to recopy it, though, in your notes, so I would recommend you do that. So here I have a reaction, and what do I know? I have the initial partial pressure of the phosphorus pentachloride, of course 5 for penta, is 189.2. And it's in an empty flask. So basically, if you think about this as a reactional perspective, reactional, is that a word? Is that you're just putting the PCl5 in here, and it's going to equilibrate and make this PCl3 and the Cl2, but initially there would be none of each of these. All right. They only gave us one other piece of information. The total pressure when it reaches equilibrium is 358.7. So let's just kind of think of our x's. This is going to go down by x. So that'll be 189.2. This one will increase by x. This will just, of course, 1x, so that'll just be x. And the same thing with this one, so that is x. But now we have kind of an issue, don't we? They didn't give me the total K value, did they? But they gave me the total pressure. Now this actually applies Dalton's law. In Dalton's law, the total pressure is the sum of the partial pressure. So in this case, that'll be the pressure of the PCl5 plus the pressure of the PCl3 plus the pressure of the chlorine. So if we know the total pressure, which is this 358 number, I can say 358.7 would be equal to 189.2, oops, I just made a mistake, minus x plus x plus x. Now, algebraically, this is not terribly difficult mathematics, is it? So 358.7 equals 189.2. I have a negative x, a positive x, and a positive x. This is 2x. So 2x plus negative x would be just x. So if I subtract 189.2, I do not need a big calculator on this one, or solver deal. So if I take on my calculator and I take what is it, 358.7 divided by, not divided by, minus 189.2, I get 169.5. So I get x to be 169.5. Actually, if you read the question, what's it asking for? What is the value of K? But if I know what x is, then I am good, right? So the pressure of the PCl5, so the partial pressure of the PCl5 is equal to 189.2 minus that value of x, which was 169.5. So that'll be just 189.5. I'm on my calculator now. Minus 169.5. Hold on. 189.2 minus 169.5 yields 19.7. And then the partial pressure of the PCl3 is the same as the partial pressure of the chlorine, which was x, which is 169.5. Now the overall K, or the Kp, of course, is the partial pressure of the PCl3 times the partial pressure of the chlorine divided by the partial pressure of the PCl5. All 1 to 1 to 1. So this will just be 169.5, the same number, so squared, over 19.7. So the equilibrium constant, 169.5 squared, divided by 19.7 gives me 1458. Or we'll call that 1460 in sig figs. So folks, that's it. It's not terribly difficult. If you get one of these problems with the total deal, the whole total deal, this is the key thing right here, is that this number right here, these all add up to the total pressure. So that's the tricky part about these problems. All right, you're going to do lots of problems in class. If you're watching on internet land, your teacher better assign you lots of problems. You need lots and lots of practice on these. But 3 examples, you can do these, you should be fine. All right, last thing in Chapter 13 as we discuss equilibrium, we want to learn, think of this more of a conceptual perspective. And we're going to talk about what's called Le Chatelier's principle. All right, what is Le Chatelier's principle? Well, when a system at equilibrium is placed under stress, it will shift to relieve that stress. What kind of stress can you apply? Well, you can apply a temperature shift, a pressure shift, or a concentration shift, or a stressor. So if you change the temperature, that will affect the equilibrium. If you change the pressure, it'll change the equilibrium. If you applies the concentration, then you'll see some kind of a shift. There's also some other ones we'll talk about. We'll talk about adding some noble gases and stuff like that, but they actually don't shift it. So we'll talk that through. All right. All right. Actually, I said that. I said that just a minute ago. Stressors do not include adding a catalyst or an inert gas. Actually, I should have said inert gas or a catalyst. That's all right. That's why I had 2 spaces. Inert gas and then catalyst. Okay. The only way to change the value of equilibrium constant, Mr. Sams? That's right. It's to change the K, or the temperature. Mr. Sams actually isn't here. He had to step out, so I'm finishing the podcast. It's the temperature. Okay. All right, what if you add and remove chemicals in the reaction? Adding chemicals in the reaction will shift the reaction away from the side of the reaction. Removing chemicals will shift it towards. All right, so this is actually what happens when we add and remove chemicals. So this is very cool as we add or remove chemicals. So what I want to do now is I want to do a demo. Okay. So what I have here on the screen, as you see, is I have some iron 3 chloride, but the only thing that's important is I have iron 3 positive, and that's going to react with the clear chemical right here, and that is ammonium thiocyanate. Thiocyanate is SCN negative. And so what I want to do is this sets up an equilibrium deal, and it makes a complex Fe SCN6, and that would be 3 negative. This color, it might just be FeSCN negative. Let me check. Actually, I was wrong. It's FeSCN and then just 2 positive. All right. Now, if you look at the iron right here, the iron, of course, has kind of an orange color, right? And the thiocyanate has a clear color. So now what we're going to do is into the dish right here, we're going to put some of both, and we're going to watch and see what happens. So I'm going to add some iron to my container, and actually there must have been some other chemicals there because it just, here, let me pause this and clean this out, it'll be better. So let me add some iron to my Petri dish here, and you can see it has this kind of orangish, yellowish color. All right. So this is just adding extra Fe3 positives. Now let me take the SCN, and I'm just going to kind of add a drop. Now if you look carefully, if you notice what's happening is it's just turned sort of a blood red color. And so the color of the FeSCN is blood red, if you will. So if I add another drop, what I'm doing is I'm shifting the equilibrium to the right right? So I add another drop and another drop and another drop and another drop, and I have shifted the equilibrium to the right. If we go back to our boys and girls and couples analogies, if the boys are the iron, right? The boys are the iron right here, and the girls are the SCN, the blood red colors are the couples, right? And so what you can do is if you add more of one chemical, it will turn it more of the blood red. So if I add more iron to this, I should get even a more, actually, no, I add the iron, yeah, it's kind of, we just don't have enough girls, if we will. So if I continue to add these, you can see how much darker and darker it gets, where we're now making more and more and more and more couples. Okay? And so we have shifted this reaction that we have here to the right. So we have the blood red color here, but we can also shift the equilibrium back in the other direction. Now, how would we do that? The answer is we can take away one of the other chemicals. So I have another chemical that really, really likes, it's also a clear chemical, that's likes Fe3 positive. It's hydrogen, dihydrogen phosphate. And so if I add a drop to this, if you notice, the color is starting to lighten up, the blood red color. And see what's happening is it's taking away. Think of this as a bunch of girls showing up to the dance, and they're prettier than the girls, the SCN girls. So if I continue to add this, all right, what's actually going on, here, let me write this out, is the way we're taking away, I'm adding H2PO4 minus to this to make another chemical. It's not important what that is, but it's reacting and taking this away. And if you take away the boys, there's no longer any boys to react with the girls to make couples, so therefore the reverse reaction gets favored and the number of couples diminishes. So if I add more and more of this, it's going to just turn lighter and lighter. I bet I got enough there. If I swirl it around, now boom, it's just the kind of the, yeah, there's still some couples there. So let's add some more. If I add more and more and more, if you will, prettier girls than the thiocyanate, it lightens up significantly. Now we're about at the same color as that. But let's say that we have some more thiocyanate show up. No, it's not thiocyanates. That's not going to do anything, will it? Yeah, no, there's still some. But if I add some more iron back, this should darken it back up, and we start seeing more of the blood red color back. So I can shift this equilibrium, there we go, back and forth, and we can go, yeah, now we've got the blood red. I can add some more of this. It clears it up, and we can shift the equilibrium back and forth. And back and forth. So hopefully you're seeing this, how we can make this go forward by adding more reactants. But the way that you take away a chemical is you have to find something it's more attracted to. In this case, it was the dihydrogen phosphate. Okay? All right, so now when I add chemicals other than those in a reaction, what usually happens is they usually have no effect on the equilibrium. Now, there is an exception to this. However, sometimes adding a chemical will, sometimes adding a chemical will react with a chemical in a reaction, thus taking the chemical away from that reaction. That's the example we did just here a minute ago with the adding the dihydrogen phosphate, shifting this reaction to the left. Okay? Now, what about temperature shifts? Temperature shifts. When heat is added to a system, the reaction will shift away from the side of the equation where the energy is. Okay? So if you have an exothermic reaction, you've got A plus B turns into C plus 200 kilojoules. That would be an exothermic reaction. Increasing the temperature will shift the reaction to the product side. No, that's not correct. It'll do the reactant side. Because if you add energy, it will shift in this direction. And the reverse is true. If I've got a reaction, energy, 200 kilojoules or whatever, plus, A turns into C. If you add energy to the reactant side, it'll shift away. So really it's kind of like adding a chemical. It'll shift to the, did I say reactant? I mean product side. Okay? All right. When pressure is increased, this is an important part. So this applies to equilibriums that involve gases. If you increase the pressure, it will shift toward the side of the reaction with the least number of moles of gas. I'll give you an example in a second. And of course the opposite is true. When it is decreased, the reaction will shift toward the side of the reaction with the most or greatest number of moles of gas. So if I take that reaction we just did on a problem earlier, PCl5 turns in, and that's a gas, turns into PCl3 gas plus chlorine gas, Cl2 gas. If I were to increase the pressure, this side has 1 mole of gas. This side has 2 moles of gas, right? So if you were to increase the pressure, it would shift in what direction? Think. That's correct. It will shift to the left, producing more PCl5 because there is only 1 mole of PCl5 versus 2 moles of gases on the product side. All right. What about adding an inert gas? Sometimes they'll say, what happens if you add nitrogen gas or you add a helium gas or some inert gas? The answer is there will be no shift. But it's kind of a trick question that is often put in the exams. Or if you add a catalyst, it will shift the equilibrium? Not at all. No change. Okay. Now, catalysts will speed up the reaction. It'll cause more boys and more girls to react and make couples, but it'll also have more couples break up. So it will speed up equilibrium, but it will not cause more reactants or more products. It will not shift. Okay, here's a classic example question. All right, here's a reaction. Oh, we need a double arrow here. Main mistakes alive. All right, so we've got a reaction. What will happen to the reaction if you remove water? Now they're all gases, right? Gas. So if I remove water, let's rewrite this. CH4 plus H2O, double arrow, CO plus 3H2. So if I remove the water, this will shift this reaction to the left, or you will make more reactants. If you increase the temperature, increase the temperature. Well, first of all, I'm looking at this question and I don't see if we could determine that. Let's assume that this reaction is exothermic. So let's say it's plus 100 kilojoules or some energy unit here. All right, so if it's exothermic, plus E up here. So if I were to increase the temperature, that means adding energy, it will shift away from that energy. So if you increase the temperature, assuming I'm correct and that this is an exothermic reaction, it would shift to the reactant side. Or we could say more reactants. What if I add helium to this? All right, helium, CH4, water, CO, H2. Guess what? Helium's not in the reaction. That's adding an inert gas. There'll be no change. All right, what if I add some remove some CO? Well, if I remove something, I take it away, it will shift to compensate for that. So it will shift to the right, or you'll make more, products. And if the volume is tripled, now when volume goes up, this is actually a tricky question, the pressure goes down. So lower pressure means it will go to the side with the least or the most moles of gas. Let's take a look at that. So if the pressure goes down, what do we say? If the pressure goes down, it will go to the side, decreased, the most moles of gas. So which side has more moles of gas? This one has 2 on this side and 1 plus 3 or 4. So it'll go to the side with the most moles of gas. So this will shift to the product side. Now, by the way, if you had the same number of moles of gas, 2 and 2 or something like that, you would get no change if you increase or decrease the pressure. Okay? Well, folks, we are now done with podcast 13.2. And this is Mr. Bergman. Mr. Sam's had to leave, so you were stuck with me at the end. So I hope you are having a great day, and we will see you in the land of the internet. Goodbye.